There is no perfect one set of settings that'll just magically work for everyone. That's not what this video is. Instead, what I'm going to be sharing is a set of ideas I've come up with to try and help you find your own settings. I'm also going to share some ideas that I think should be implemented by devs to hopefully improve the gyro experience. If this happens to be your first exposure to gyro, I'm going to go ahead and break down the basics. So the first thing I'm going to go ahead and cover is just basic gyro rotation and how it correlates to in-game rotation. There are 3 axi that you need to keep account of: yaw, pitch, and roll. This is what yaw looks like. Next is pitch. These are the only 2 types of rotation you really have to deal with when it comes to first-person shooters. But with the power of cheap editing, this is what roll would look like. So next you need to learn how cameras work in first-person shooters. Basically, yaw rotation is fixed at a pitch of 0. What this means is that regardless of how high up or down you look, yaw rotation is always going to be fixed at the horizon. Keep in mind that I have not tilted my controller up. This will be important later in the video. If you think about it, first-person shooters are using tank controls, because your camera rotates around like a tank turret. Now this is useful because this is how we calibrate sensitivity for gyro. Whether you're setting up gyro or flick stick, there is a really simple rule that I think you should follow. You want your dots per 360 to be as high as possible while keeping your in-game sensitivity as low as possible. To show you why, I've set up this example. Here, I have a low dots per 360 of 720 with an in-game sensitivity of 10. Now what you're going to see is that the crosshair in-game is going to be skipping exactly half a degree. So even though the gyro is perfectly calibrated, it looks like your camera is skipping around the screen. Mouse players wrongfully call this pixel skipping. You are not skipping pixels, you're skipping angles. This is angle skipping. And now, with a high dots per 360 and a low in-game sensitivity, our gyro will now be skipping exactly 0.01125 degrees. Now, I tried my best to spin this by hand, so that's why it's not perfectly smooth. But you should see that it is smoother. In fact, there's actually a hard physical limit that your eyes can actually see the skipping, but I'm getting ahead of myself. So next, I need to show you how to actually find these sensitivities. All you gotta do is use mousesensitivity.com. What you need to do is change your units to counts. Then pick your game and type in a sensitivity. This is the exact value that you'll need to use in Steam input. You'll also need to check and make sure that the game doesn't have smoothing, acceleration, or FOV scaling. Otherwise, you'll have to compensate for that. Now, not every game is going to give you an exact perfect value that you can just plug directly into Steam input. Sometimes you'll wind up with decimal values. Apparently, Steam input can accept up to a decimal place of 2, but I didn't know this. Now, Now, for context, I used to modify VDF files directly before Steam inputs new UI. So I was under the assumption that you had to use an exact count value. And that's why I went ahead and made something pretty stupid. This is my gyro tool spreadsheet. This is something that I started working on for myself, as I wanted angle perfect calibration for all of my games. I figured I could just use math to find all of the best combinations of sensitivities. Over time, I started adding other calculators to this as well, which is what I'm going to be walking you through today. Alright, so just like mousesensitivity.com, you're just going to pick a game from the drop-down list. Here I have AimLab selected. And then you're going to pick in-game or config calibration. Now on the left here is where I've listed every game that works with my calculator. I'll explain that in a bit. But essentially, I've listed them in a color-coded system to tell you whether or not there's smoothing or things that you need to disable. So here I've put some resources that you can use to remove those settings. Mouse sensitivity usually tells you how to remove these things, but if mouse sensitivity doesn't have any options, you should check out the PC Gaming Wiki. Now, on the right, after you've selected a game and your in-game sensitivity, these two lists will automatically fill out with the best possible sensitivity combinations. On the left, in these two columns, is every single perfect calibration, and on the right is every single near perfect calibration. So for example, as you've seen earlier, I was using a sensitivity of 32,000 with an in-game sensitivity of 0.225. If a game does not have an exact perfect calibration, you'll want to look to this list. So the next best sensitivity you could possibly use is going to be at the very bottom here. Just look for the numbers that are highlighted blue. Numbers that are highlighted green are usually the absolute best. What you want to do is you want to look for the sensitivity with the most zeros in it. So this value right here would be the best sensitivity. In Steam input, you would use 31,718, and in-game, you would use 0.227. This will give you basically perfect calibration, where you will not notice any miscalibration whatsoever. If you plan on using Joyshock Mapper or Rewazd, you can go ahead and bring your sensitivity over to this converter here. It converts both flickstick and gyro since they're the exact same thing. For Rewazd though, there's two sensitivities, one for flickstick and one for gyro. And to calculate a specific gyro ratio, you just type that ratio here. Now, some games have FOV scaling. I've selected a game here that has FOV scaling to show you that it automatically gets loaded up into this converter. All you have to do is type the FOV you want to play at. Now, there's two types of FOV scaling, linear and focal length. For the most part, you want to use the linear sensitivity. If that doesn't work, try the sensitivity below. And just like the converter above, you can calculate your gyro ratio here. Now, I realize there is kind of a big problem with this, and it's that because the sensitivity is getting rescaled, that means the perfect calibration does tend to get lost. Which is why, while I was making this part of the video, I suddenly realized I could just math it. So, if you scroll to the right here now, you can see I added two new sections. So now you can just look through these lists to find the best sensitivity. So like I explained earlier, you want to use linear, and if that doesn't work, try focal. So there's actually a lot of games missing from my list, and that's because my calculations only work with linear scaling. I have a separate sheet for the games that are missing. On this sheet, pretty much every game here is a console game that was ported to PC. So all of these games have different kinds of scaling that just doesn't work with my calculator. So for these games, I've decided I'm just going to do things the hard way, and I'm going to manually list the best sensitivities I can find for all the games that I own. Now, before I get onto the next calculators in my sheet, I need to teach you about gyro orientation. At the beginning of the video, I showed you how game rotation works. Now, I'm going to explain to you how gyro orientation works in context of that. Steam input gives us all of these options. I'm going to walk you through each one. And I'm going to explain to you what the ultimate goal of all of this is. Starting off with yaw. So like I showed at the beginning of the video, if you're pointing your controller at the screen, yaw rotation looks like this. Now, watch what happens when I pitch my controller up and do the exact same motion. As you can see, nothing at all. This is because yaw rotation remains relative to the controller. And the same thing is true for pitch. Next, under each gyro style, is an option to rotate the output. All this means is that we're reorientating the gyro output on the rolling axis. The gray controller represents the gyro's true orientation, while the red controller would be your actual controller. And now for roll. With the roll style selected, our horizontal rotation is now controlled by the roll axis of the gyro. This also means we no longer have yaw. And just like yaw, pitch stays exactly the same. So just like I showed with yaw, I want to show you what happens when I pitch the controller up. Roll has effectively become yaw, although the output is inverted. Rotate output on roll works a little differently, because it actually looks like this. So next, what if we simply combine yaw and roll? So to start off, pitch is still pitch, but now we have yaw and roll. Now, this style gives us a new option to adjust, the roll axis contribution. This controls which direction rolling our controller will yaw our camera in-game. At this default, rolling works exactly the same way as I've shown it before. At 0%, you're essentially just using yaw, and there is no roll input whatsoever. And at -100, the rolling action is completely reversed. In fact, I think this should honestly be the default, and to show you why, I'm going to remove the pitch axis for this next example. Now, if you remember, pitching up the controller changes yaw to roll, and roll to yaw. With our current settings, I want you to see what happens. As you can see, the camera is now essentially synchronized with our real physical motions. So this creates an interesting scenario, because unlike mouse where you would have to increase your horizontal sensitivity to extend your range, with this setup, you can extend your range without technically increasing your sensitivity. You do have to keep in mind though, that because yaw and roll are on at the same time, this does negatively impact horizontal precision, especially at higher sensitivities. So it's not ideal, and there's a reason why more gyro styles exist. So for this style, both rotation methods are used, which looks like this. To give you some perspective as to why you might want to do this, imagine you're lying sideways on your bed, and you're holding your controller like this. Would this be a good idea to actually do? Probably not, but you can do it. Up next is local space. It's essentially the same thing as yaw plus roll, except there's one more setting that we can adjust. This is the primary axis offset. It's very similar to rotate output, only this time we're changing the relative yaw output on the pitch axis. For this next example, I'm going to go ahead and disable roll and pitch, and I'm going to use a setting of -90. I imagine you could use these settings if you're using a Steam Deck and you're lying on your back. Alright, before I move on to the next three styles of gyro, I first need to teach you about gravity, and the factor that it's going to play into these next three styles. You see, the last four styles all ignore gravity. To clarify what I mean by this, I'm going to go ahead and switch back to yaw and give you some examples. So what you got to understand about the last four styles is that output is always relative to the controller. And so it doesn't matter what position you hold the controller in, yaw is always going to be yaw, and pitch is always going to be pitch. So for example, I could hold the controller upside down, this is still pitch, and this is still yaw. I could hold it sideways like this. This is still yaw, and this is still pitch. So it literally doesn't matter how you hold the controller. The gyro output is always going to be relative to the controller's perspective. And since you're holding the controller, you can think of this as your local space. For maximum consistency though, what we want is for yaw and pitch to be consistent not with the controller, but with our physical motions, regardless of how the controller is being held. And we can do this by factoring in gravity. To show you how this is done, I'm now going to show you how player space works. For the next examples, I'm going to temporarily disable the pitch axis. Alright, so remember what I showed you about roll becoming yaw, and the problem being that both axi are on at the same time? Well, watch this. In just about every controller, that's not Xbox, we have a gyro and an accelerometer. Conveniently, the accelerometer can determine the direction of gravity using it as a fixed point of reference. Combining that information with the gyro sensor, we can ensure that yaw rotation is always relative to gravity. So how does this work? Here I've set up a visual metaphor of what's going on. So above, we have our controller as usual. Now, imagine that you have a sphere connected to it with a string. It doesn't matter what position you hold the controller in, the sphere is always going to be aligned with gravity. So we use the yaw rotation of the sphere instead of the controller. And that ensures that we are synchronized with the game world. So you can think of it as the world space, because we're synchronizing the real world with the game world, thanks to gravity. However, this style is called player space. And to show you why, I'm now going to re-enable the pitch axis. So for this style, we are only synchronizing the yaw rotation to the real world. The pitch axis, however, is still relative to the controller's local player space. As you just saw though, this can be problematic because if you roll your controller too much, we lose yaw rotation entirely. This also has a negative impact on rotate output if you're trying to do the sideways controller thing. Although to be honest, I don't think you should be using rotate output with any of the gravity-based styles. Next up is world space. From my knowledge, this is a style that you'll most often find in Nintendo games. So just like player space, yaw rotation is based on gravity. The difference this time is that pitch direction affects yaw rotation. So, vertical pitch looks normal. However, if I pitch my controller 45 degrees, there is a problem though, and it becomes obvious at 90 degrees. So the problem here is that the more we roll our controller, the more we lose pitch. So this style has the exact opposite problem of player space. The more we roll our controller, the less pitch we have. And again, here's rotate output. And finally, we're at our last style, laser pointer. So Valve says that this style is best suited for 2D games like rail shooters. The thing is, the way this style actually works means that it's perfectly suited for 3D games as well. In fact, I think there's a better way to achieve what it is they're trying to do here by modifying another style that already exists in Steam Input. Except, I'll explain that later in the video. Remember the sphere example I showed earlier? Well, this style works almost exactly like that. As you can see, we have almost near perfect synchronization. And I say almost because there is one drawback. Even though I'm pitching my controller 90 degrees, we're only traveling about 60. To be honest, I don't fully understand why this limitation exists. I think it has something to do with the world space, but I'm not sure. So to give you a bit more understanding of how I see things from my perspective, here's another example of how gravity works. So remember, pitching up the controller changes roll to yaw, and yaw to roll, which means what we're actually doing is we're disabling the axis that is parallel with the direction of gravity and enabling the axis that is perpendicular to the direction of gravity. So what laser pointer seems to be doing is that it's factoring in two more details. As we roll our controller, not only does yaw become pitch and pitch become yaw, we also need to change the output of each axis relative to gravity. The next thing that laser pointer does is what I think is causing the limited vertical range. You see, as you pitch the controller up, yaw changes into pitch. Essentially, we're landing in the exact same position as rolling the controller. It's just a matter of perspective. So unless you try to factor in a magnometer to try and tell which direction the controller is facing, which not all controllers have, by the way, I'm not sure it's possible to determine which pitch axis you should have on at a given time. So I'm not sure if the vertical scale problem can be fixed, but if it can, then in my honest opinion, I think that laser pointer would be, and kind of already is, the best gravity style. And one last time, here's rotate output. When it comes to setting up gyro in 2D games, what we essentially want to do is to simulate the feeling we experience when we play 3D games. The best way to do that is to try and replicate the settings that you use in those 3D games. So here, I've provided two different options for you to choose from, and I'll explain to you the difference. Starting off with what I call Rubberband simulation. So to begin, you first need some key information about your games. Starting off with your screen, you're going to need to know what aspect ratio your screen is. On average, most screens are 16 by 9. Here, I've listed off various common aspect ratios, but you can edit this and add more if you want. The next thing you need to know is what FOV you're playing at in your game. And what I mean by that is whether or not the game uses vertical FOV or horizontal FOV. To find out, you should look your game up on mousesensitivity.com or PC Gaming Wiki. And if you can't find that information on either of those sites, I've also included a link to a very useful tool that I use to find the FOV in any game. So I did not make this, but I have been using this for a very long time now. It may look complicated, but all you have to do is take a screenshot of your game, drop it in here, and then align the blue line to the horizon. And then you want to find a square object and match these red lines to that square. And to ensure you match the correct shape, you have two more settings to adjust those lines. And this will give you the FOV on the left. This first setting here is your vertical FOV. So this game has a vertical FOV of 71 degrees. And this setting at the very bottom tells you that the game has a horizontal FOV of 104 degrees. The middle setting is telling you the horizontal FOV at a 4:3 aspect ratio. You don't really need this, you could ignore it. A typical rule of thumb you can follow is that if a game is defaulted to 60, that's usually vertical FOV, which is actually an FOV of 91 degrees. If the default is 90, then that's usually horizontal FOV, which is a vertical FOV of 58.7. Now, not all games are this straightforward. For example, Apex Legends says that it uses an FOV of 90. However, this is 90 at a 4:3 aspect ratio. So if we convert this horizontal FOV to 4:3, that means we wind up with a much higher FOV. So taking the converted vertical FOV from this section, you can copy and paste this into the vertical FOV settings to see what the true FOV is. And as you can see, a 90-degree FOV in Apex Legends is actually 106. So be sure to look up your games on mousesensitivity.com or PC Gaming Wiki to see what kind of FOV your game uses. Once you've filled out either of these sections, we can now move on to what I call rubber band simulation. First, you're going to pick from either the vertical settings or the horizontal settings. I'm going to leave it at vertical for now. Next, you need your screen resolution, just your vertical resolution. So I have a 1440p screen, which means vertical pixels is 1440. Next, you'll need your gyro ratio, which you only really need for ReWASD. And after that, I have this setting. It's rare, but sometimes the calculations can exceed 32,000 dots per 360. So if you ever need to reduce that number, that's all that this is for. So for example, if I type in 2 here, the updated settings are now exactly the same, but just different numbers. And that's all this is for. For the most part, you can just leave this at 1. And the last thing we need to take into account is Windows pointer speed. If you don't know what this is, I'll show you in Windows how to adjust this. But for the most part, this default setting should be fine. Now let me give you a visual example of what's going on here so I can explain to you the numbers on the right. Here we are looking at a horizontal FOV of 90 degrees. The goal we're aiming to achieve is to simulate the sensation we experience when our crosshair travels to the edges of the screen from a starting point of 0, 0. Now in AimLab, the crosshair isn't perfectly centered on 0, 0 because your character's head is actually above the yaw horizon. But with that in mind, this is the yaw axis we're going to match, the pitch axis, and the diagonal axis. So starting off with the yaw axis, this looks like a straight line. However, if you look at the world space from a top-down view, it's actually curved. And from this point of view, we can see the relationship that this curve has with a flat 2D screen. So in this example of 90 degrees, we are calculating the distance needed to travel across 4 screens in flat 2D space. And this in turn gives us a sensitivity that reproduces the distance of travel for your crosshair in a 3D game at the horizon. I call this rubber band simulation, but this is exactly the same thing as linear focal scaling. So regardless of how far away you're sitting from your screen, your 2D gyro is always going to feel similar to your 3D gyro. So I used to just leave it at that. I would only calculate the horizontal sensitivity. That is until I realized that vertical sensitivity has a completely different relationship to the vertical pixels of your screen. The same is true for diagonal, which means we need to take all 3 directions into account. So back to my calculator, I've given you 2 options to choose from. The first option, and the one I recommend you use, takes the average of all 3 directions to give you a nice, simple, clean number. The second option is to calculate horizontal sensitivity and vertical sensitivity separately. This is something you'll have to try for yourself, because remember, these settings are all about replicating what you feel. So you want to use what feels best to you. In case you're wondering, these black boxes are just extra calculations that I'm keeping hidden. So if you want to know what the full math is, you can go ahead and look at that. So that's my first calculator. And this one is all about simulating what you feel. The next calculator is about simulating exactly what you experience. So I call this next style Wiimote simulation, because that's exactly what we're going to try and do. So just like the other style, we're going to need your aspect ratio and screen resolution. But on top of this, we're going to need to know how big your screen is. If you didn't know, most TVs and monitors are sold by the diagonal dimensions of the screen. So if a screen is being sold as 32 inches, that really means it's 32 inches diagonally. Next, we need to know how far away from your screen you're sitting. I've set this up in centimeters, but I've set up some automatic calculations below to show you the same distance in meters, inches, and feet. Just like the other calculator, you'll need your gyro ratio. And again, I have the reduced dots per 360. For my other calculator, it's rare to exceed 32,000 dots per 360, but with this one, depending on how far away from your screen you're sitting, it is very easy to go above 32,000 dots. And there you go. That's all this is for. So now, let me show you exactly what we are doing here. In this example, you'll be able to see the relationship that controller rotation has to viewing distance. Imagine that there's a laser emanating from your controller. If you point from one side of the screen to the other, there is a certain viewing distance where that rotation is equal to 90 degrees. Now, watch what happens as you move away further from the screen. What you're seeing here is the exact same principle as focal length scaling, since we're factoring in the distance to the screen. As you can see, our FOV decreases. In order to correctly point at the edges of the screen from this new viewing distance, we need to increase our sensitivity. This is represented by the circumference of the sphere. So that's basically all there is to this style, although we do need to factor in the vertical scale. So unlike the other style, you will need to lower your vertical sensitivity based on the settings you're using. And once that is done, we will be synchronized exactly with the horizontal and vertical axis of the screen, which brings me to my next idea. You see, there actually is a third option. It just doesn't exist yet, at least not fully. So this next part is for any developers that might hopefully be watching this video. At the bottom of my sheets, I have a page called Screen Space Gyro, so I'll now cover that next. All right, there's a lot of numbers on this page, so let me walk you through what I'm doing here. On the left, I'm once again just calculating the vertical and horizontal sensitivity you would need to simulate a given FOV on your screen. Next to that is just some math that I'm using to help me calculate the relative FOV based on where you're looking at the screen. So you can think of this graph in the middle as your screen, and the lines represent the FOV curvature. By the way, small tangent, only flat screens are capable of showing FOV curvature correctly. So I hate to break this to you if you're watching this on one, but yeah, curved monitors are mathematically a gimmick because they exaggerate and distort the FOV curvature of 3D games. Anyways, tangent over. And here, I'm showing you the sensitivities you would need based on the position of the mouse on the screen. Let's say your mouse is at the center of the screen. This means, for horizontal sensitivity, you would need to use this sensitivity. Because at the center of the screen, the FOV is equal to 90 degrees. As our mouse moves down the screen, or up, the relative FOV decreases, which means the sensitivity we now need to use is this, because as we approach the edges of the screen, our FOV decreases. The same is true for vertical. At the center of the screen, we use this sensitivity, and as we move left or right, the vertical FOV decreases, which means this is the sensitivity we now need to use. So this is the math you would need to do if you actually wanted to create a proper laser pointer mode for gyro, essentially replicating what the Wii did with a couple of infrared lights and a camera. Except there is a problem with this. Without a fixed point of reference to use, it's impossible to tell at what horizontal direction the controller is being pointed at to scale the vertical sensitivity. However, it should be possible to scale horizontal sensitivity based on the pitch axis orientation relative to gravity. But if we do that, then we should probably just do something that is more efficient than what I'm doing here. Because I'm not even sure if this method that I just showed would actually work, at least not the way that I've shown it. Also, I wouldn't want Valve to actually change how the laser pointer style currently works. So instead, this next part is what I'm actually going to propose. Mouse region is a style that has needed some updating for quite some time now. You see, mouse region lets you map a region of the screen to your pitch and roll axis of your gyro, using gravity as a point of reference to control your mouse with absolute positioning. I've always had a problem with this though, because you can never adjust the pitch angle that you hold your controller at. So in this example, imagine the screen is underneath my controller. In order to hold the mouse at the center of the screen, you need to hold the controller at a very awkward 45-degree angle. And it has always just made this style very clunky and awkward to use. So I've never used it, and I don't think anyone ever has used it. Which brings me to my next point on how we could probably update this to actually make it a viable style of mouse control. I actually reworked this next part while making this video, but what I'm showing here is the math you would actually need to properly map out the screen space to your controller's rotation. The only thing I'm showing here is just the relationship of controller angle to the pixel output you would need on the screen for horizontal and vertical positions. To see how this actually works, I have the settings on the right. So here, let's say we're simulating an FOV of 90 degrees. That means when the controller is tilted at a 45-degree angle, we should be pointing at the edge of the screen. And if we increase our FOV to 100, this means we're now only pointing at about 90% of the screen. We'd have to tilt our controller further to actually match the full range of the screen, which in this case would be 50 degrees. And as you can see, we get the exact same pixel position. We do the exact same thing for vertical. And there you go. If we can keep track of the exact angle that a controller is being held at, then this should give us a very realistic type of gyro control for our mouse. A true laser pointer mode, effectively using gravity like a Wiimote sensor bar. There's my idea. I'd love to know if this is possible. Although, one more tangent, I realized what I'm doing here is I'm essentially taking 3D rotation and converting it to more accurately move across 2D space in a 3D manner. And I realized, what if we did the opposite? What if we could reverse all of this and apply it to a touchpad? So that way 2D swiping on a touchpad results in more realistic rotation in a 3D game. I haven't gotten around to figure out how to do that, but there's another idea I had. Anyways, there's one more thing I need to explain in my 2D calculator, and then I can move on to explain Windows pointer speed. Underneath my 2D calculators, you'll find this calculator for a game called McOSU. All this game is 3D OS. In order to calibrate that game, you need to convert dots per 360 to centimeters per 360. So I made a converter specifically for this game, one, because it's really unique, but two, So that way you can actually test your 2D settings in a 3D game. Because this is another benefit of calibrating a 2D gyro. If you're playing a game that doesn't allow you to use Steam Input's mouse detection to have two different sensitivities, then you'll have to use one sensitivity. So let's just say, for example, let's just say we're using these settings right here of 8,335 dots per 360. So what I would recommend you do is to go over to the right and find an in-game sensitivity that is closest to that. So around this area, use any of these sensitivities and you'll be close enough. And the benefit of this is that your 2D gyro will now feel very similar to your in-game sensitivity without the need for two different sensitivities. Okay, now that that's explained, let me show you how Windows pointer speed works and how you can adjust it. All you have to do to find pointer speed is to search for mouse settings. Once here, you'll find the slider for it. This slider goes down to 1 and up to 20. However, older versions of Windows used to show this differently. Under pointer options here, you'll find the exact same thing, only it has a different slider. This one ranges from 1 to 11, with 6 being the middle. And by the way, while you're here, you should make sure that this is disabled. We do not want enhanced pointer precision. Now, let me show you what the scaling actually looks like on both of these sliders. At the bottom of my calculator, I have this showing exactly what Windows pointer speed looks like. At a setting of 1020 or 611, this is considered one-to-one input. This is because dots become equal to pixels. So that's why this is often recommended as what you should be using. However, at the beginning of the video, I did say that you want to use the highest dots per 360 you can with the lowest in-game sensitivity. So if you want to guarantee you have an even smoother experience with gyro, it might be worth using a pointer speed option of 620 or 411. Using this setting basically lets you double your sensitivity for free. So here with the dots per 360 of 1000, at this pointer speed, you would need 2000 to move the mouse the exact same distance. And if you leave your dots per 360 at 1000, you're essentially playing at 500 dots per 360. From my experience, this is the lowest pointer speed I would actually recommend. But for the most part, if you just want to play it safe, leave your pointer speed at the default. And in case you're curious, I actually realized that Windows pointer speed does use a specific pattern for its scaling. I just have to type in a specific number here. It's basically just scaling by bits. You have 64-bit, 32, 16, 8, 4, and 2. And that's Windows pointer speed. And now, since we're kind of on the topic, I'm going to go ahead and move on to sensitivity. All right, now it's time to answer the question. The ultimate question. 42. And next, I'm going to walk you through this part of my calculator that is designed entirely to help you find a sensitivity that is suitable for your playstyle, beginning with what I call the wrist arc. In order to find your wrist arc, I made a texture that you can use in AimLab as a 3D compass. I've linked it above. This is the grid that I've been using throughout this video. In AimLab, you simply have to use the sphere box map and apply this texture. Now, let me show you what a wrist arc is. In order to measure your wrist arc, I recommend that you use the settings that I'm showing here. Obviously, we'll need to play at 1:1, remove Deadzone and precision speed, and leave the mixer where it's at. I do feel that laser pointer works best, but if you're trying to do something specific, for your playstyle, then use whatever it is you're using. Now, throughout this video, you may have noticed these circles. There are 4 in total, although you can only really see 3 of them. The first circle is at 30 degrees, which totals to 60 degrees. The next is at 45 for 90, and then 60 for 120. Now the fourth circle is all the way at 180 degrees, although it doesn't really look like a circle. And I'll get to this because this is important. Now, let me switch to a hand cam mode so I can show you exactly what I mean by a wrist arc. Alright, so here, I'm holding my controller like I would in any game. My elbows are to my side, and my controller's on my lap. If I use only my wrists and I don't move my elbows, you'll see that I have a range of about 60 degrees. 30 degrees left, and 30 degrees right. And if I draw a circle, that effectively represents the range of aim that I have to work with. I call this the wrist arc, although really it's more of a wrist cone. I just think wrist arc sounds cooler. Now, if I include my arms and I let my elbows move a bit, I can extend my range to 90 degrees, or 45 degrees left and 45 degrees right. And if I hold the controller one-handed, like a Joy-Con, I now have 60 degrees left and 60 degrees right, for 120 degrees total. Although drawing a circle is pretty awkward like this. But you get the general idea. Now, the most basic recommendation to set up gyro sensitivity is to increase it so that way moving left goes 180 degrees and moving right goes 180 degrees, totaling 360 degrees. So if I use my arm range of 90 degrees, that means 45 degrees left times 4 equals 180. So I would have to play at a sensitivity of 4:1. And so now if I rotate left, we're at 180 degrees. And rotating right is 180 degrees. And this is what most people land on, is around 4:1. But now, look at what happens if I try and draw a circle. I do not have full coverage. There is this area here in the middle that I cannot reach. So that means if you only calibrate based on your horizontal sensitivity, you are not going to have full coverage. And to show you why, I'm now going to explain this in 2D. If you really think about it, shooters are actually 2D because we're only rotating on 2 dimensions, pitch and yaw. And so that means if we want our wrist arc to cover the full 3D space, we shouldn't be calibrating to the horizontal space because that just winds up looking like this. Instead, we need to calibrate to the hypotenuse. Once you have your wrist arc sorted out, you can bring your gyro ratio here. On the right, I've made a list of possible recommendations for you to choose from. This first setting is what I just showed you. We're matching the sensitivity to the hypotenuse of the game world. This next setting takes something else into account though. You see, most games only let you look 90 degrees up and 90 degrees down. This is what gives us our 2:1 aspect ratio. If we could turn 360 degrees on the vertical axis, then this is the sensitivity you would need for true full space coverage. Because we don't actually need to increase our vertical sensitivity, that's why I've included this option on the right. Using this vertical scaling, you will have the same vertical sensitivity as my first option. And now, here's our third option. What if instead of adjusting your sensitivity so it's 180 degrees left and 180 degrees right, instead you use 360 degrees left and 360 degrees right? This is the lowest sensitivity you would need to cover that full space. This next option is literally just the first option doubled, so I'm actually just going to delete this because it's not really necessary. And I guess that leaves us at our last option, which this is just factoring in 360 degrees on the pitch axis. And that looks like this. And those are my recommendations. Really, all of this is just a math-based excuse to give your aim some headroom. Because at the end of the day, I realized people can get used to literally anything, so you might as well use settings that are comfortable. And that's my advice. Now, there's another link here that I'd like to point out. Because I'm curious, and because I think this might help devs out, I linked a survey here. All this survey is asking you what your wrist arc is. I figure, since most controller games have preset settings for joysticks, maybe we should have some preset settings for gyro. And this might help us find some default settings. In fact, I have a page on my sheet showing you what I think some preset settings could look like. So at the bottom, I have a page called defaults. If you want to see what I recommend for presets, this is what I've landed on, but again, all of this is just my opinion. A question I tried to answer here is, at what setting should you actually consider using flickstick? And from my experience and my understanding of what other people use, I think around 4:1 is where you should consider using flickstick. If you're playing below that, just stick with normal joystick until you get used to gyro. And above that, you can switch to ratcheting or do whatever you want. Now next to this is just recommendations for the Steam controller, because I realized a big reason why I was able to get away with using a 3:1 sensitivity for so long was because I was using a Steam controller. Touchpads naturally synergize with gyro. And something interesting that happens, in my opinion, is that as you increase your sensitivity, you can actually lower your touchpad sensitivity, so that way your thumb pad swiping is even more precise. Anyways, all of this is just my opinion, so that's why I made the survey. I'd like to know what you think. Now, if you happen to own the best controller ever made, this next section is for you. So what I'm doing here is I've just expanded the earlier concept to the screen. So if you want to map your full screen space to your touchpad, then this is the sensitivity you'll need to use. If Valve ever updates touchpad input, then this would be the sensitivity you'd need. And if you want to lower your sensitivity to increase it with Steam Input's old mouse acceleration options, these are the sensitivities you should use with those options. Down here, I'm doing the exact same thing as we did for gyro, but this time we're doing it for the touchpad. Just put your dots per 360 here, and this will convert it directly to a mouse percentage, with acceleration options to the right. And if you want full coverage, this is the sensitivity you'll need to place the entire world space onto the touchpad, with mouse acceleration options on the right. Now, I would like to take a small tangent here. These calculations are just another reason why I believe round touchpads are objectively better than square. Yes, technically, a square touchpad does map the full space to the pad. However, most players don't actually swipe from one edge of the pad to the other. This means you need to increase your sensitivity anyways to give your thumb some headroom. And so combine that with the fact that a round touchpad is a lot more intuitive if you're simulating joysticks, especially for joystick movement. And well, that, in my opinion, is just objective proof that a round touchpad is the better shape. After all, why is a soap bubble round? It's because round objects are the most energy efficient configuration in the universe. Alright, tangent over. Now we can get back to gyro. Alright, for this next part, I want to try and give you a deeper understanding of the relationship that both FOV and sensitivity have to the real world. So this next calculator is actually a two-part calculator. This first part is exactly the same as the Wiimote calibration, which is also the exact same thing that racing sims use to calibrate their FOV. So if you were to use the FOVs that are listed here, your screen would now feel like you're looking through a window, as everything in the game rolled will now have the correct proportions relative to reality, unless of course you're on a curved monitor. And so next to this, I went ahead and added something that should be useful for gaming in general. Have you ever wondered if you actually need a 4K TV or screen? Well, with this, you can find out, because the truth is, human vision has a hard limit. That limit is about 1/60th of a degree. So depending on how close or far away you're sitting from your screen, your eyes literally cannot tell the difference past a certain resolution. So for example, with the settings I'm using here, I could lower my in-game rendering to about 77%, and in theory, my eyes would not be able to see any difference at all. So if you're using FSR or any kind of upscaling, I'd recommend using these settings. And so I can show you what happens as you move closer to the screen. The closer you move to your screen, the higher resolution you need to fool your eyes into perceiving a smooth image. Now, once we have that set up, we can move on to the next part of the calculator. So down here is something that I came up with to try and measure two things. The first is whether or not you can actually perceive the angle skipping with the settings you're using in game. The second is the relative shakiness of your crosshair that you perceive in the game versus real life. So to use this, all you need is your FOV, dots per 360, and your gyro sensitivity. And on the right, you'll be given these three ratings. This first one is a rating for angle skipping. You want this number to be above 60. This is because 1/60th of a degree is the limit of human vision. Next is perceived shakiness. Essentially, what I'm showing here with these two settings is how shaky your crosshair is relative to real life. You see, because your FOV is higher than a realistic FOV, this condenses the visual space down, hiding the shakiness that you would perceive in real life. So with these settings that I have here, even though the gyro is calibrated to a sensitivity of 1:1, the perceived stability makes you feel like your crosshair is 3.4 times steadier than real life, even though it isn't. Again, this is all about perception. So if I increase the gyro ratio to 3.4, and so now at this sensitivity, your crosshair would have the same shakiness that you would perceive if you were to hold a laser pointer and point it at your screen. And as we go to higher and higher sensitivities, the perceived steadiness gets worse and worse, which is an obvious given. So by increasing the sensitivity to 10, your crosshair is now basically 3 times shakier than real life. And again, this is all perception. Your crosshair is literally 10 times shakier than real life, but perception-wise, at the current FOV, your crosshair is 2.8 times shakier than real life. If you were to actually use a realistic FOV, however, you would see that your crosshair is indeed 10 times shakier than real life. Now, let me show you what this looks like using AimLab. Okay, for these examples, Faith is going to be our point of reference. Here, I'm using a vertical FOV of 60 degrees. Now, instead of holding the controller in my lap, I'm actually going to hold it in the air as if I were actually trying to aim, just so you can actually see the shakiness. In this footage, I have scaled the vertical FOV down to 6, so by a factor of 10, and I've also scaled down the sensitivity of the gyro to 0.1. In this footage, I've reverted the FOV back to 60 degrees, but I've increased the texture size of the world by 10, and I've also increased the sensitivity to 10. So now, with all three examples side by side, you can think of the left example as you being close to the screen with a low sensitivity, and on the right, you are far away from the screen with a high sensitivity. And thanks to relativity, all of these settings look exactly the same. So here's one more example that's going to be related to the next section of the video. On the left is a sensitivity of 1 with a low FOV, and on the right is a sensitivity of 10 at a standard FOV. Without linear FOV-based scaling, both of these settings look exactly the same. Alright, before the next big part of the video, let me break down the other thing that was in my sheets. In this area down here, this is just a simple calculator that uses the same math and recommendations as the film and television standards for the recommended viewing distances. So if you want to know how far away from your screen you should be sitting, you can use this to find out. Although this isn't a hard rule, it's just a basic recommendation. If increasing your sensitivity is the only way to make gyro comfortable, then that's a problem, because doing so sacrifices precision. And on top of that, the shakiness of the camera can just make things unbearable. So then, what options do we have in order to counter the shakiness? Smoothing introduces too much input latency, so I'll be honest, I don't actually recommend it. And Steam Input's current options, well, they're interesting, and I'll get to them. But first, I need to teach you about the option that I settled on, mouse acceleration. There are 4 pages at the bottom of my sheets, all titled Something Gravity. To teach you about mouse acceleration, I'm going to start off with the most simple one, linear. To begin, I've set up this visual example to show you what linear mouse acceleration actually looks like. On the chart here, the horizontal axis would represent how fast your gyro is moving in degrees per second. The vertical axis represents your sensitivity relative to that speed. So if you're not moving your gyro at all, your sensitivity is basically equal to 1. And as you move faster and faster, your sensitivity will increase to 4 until it flattens out. This is essentially the exact same thing that stabilization is doing, by the way. The difference is, stabilization lowers your sensitivity all the way to 0. Most mouse acceleration programs can't actually do this due to the way that the math is actually being done. So stabilization is technically different from Accel because of that little detail. So while I'm here, I can show you what Steam Input's first option actually looks like, the Deadzone setting. If you use Steam Input's Deadzone option, this is basically what you're doing. You're creating a speed limit where input is lost entirely, creating a dead zone. And I'm going to be blunt, this feels terrible. I do not recommend it for gameplay. And likewise, I feel there are problems with lowering your sensitivity all the way down to 0, because I've learned to think of sensitivity as gravity. So let me explain. At a calibration of 1 to 1, your gyro is synchronized with the game world, which is synchronized with the real world. So imagine that this line represents you existing on a certain plane of reality, kind of like gravity. And as you increase your sensitivity, you're essentially making yourself lighter and lighter because it takes less energy to move a farther distance. So using 1 to 1 as a reference point, that means as we go below 1 to 1 as a sensitivity, if we want to make ourselves 4 times heavier, then we would lower our sensitivity to 0.25. Because now we are exerting 4 times more effort to travel the same distance we would at a 1 to 1 sensitivity. And so that's why I made this converter here. I originally had a recommendation here for target counts, meaning degrees per second, but I actually removed it because I'm basically trying to standardize time, and that's pretty hard. Although I do think I've come up with something, but I'll have to show it to you later. So the way this works is that you just choose your gyro ratio like you normally would. On the right here are recommendations for your starting sensitivity. This is meant for games that have native gyro implementations like Fortnite. So in Fortnite, what you would do is you would set your base sensitivity to 0.25, and then using acceleration, you would use a multiplier of 16. This will give you a 4:1 gyro ratio without lowering your sensitivity all the way down to 0. So in a game like Fortnite, if you want to simulate the settings I just showed, this is what you would do. You'd lower your sensitivity to 0.25. Although, I guess Fortnite doesn't let you do that because it moves in increments of 0.02. And then your acceleration multiplier would be 16. And since I'm using spreadsheets, I figured I'd try and come up with some other suggestions. So I came up with a median sensitivity. This is the median point between 1:1 calibration and your target gyro sensitivity, with the necessary multiplier below that. If you happen to have raw Accel and are using it with ReWAS, these are the settings you would need to use in raw Accel to simulate the settings on the left. So I've set this up for the natural curve and the linear curve, since in my opinion, those are the only two that really matter. And be sure to type in the base gyro you want to simulate before using these numbers. From what I understand, raw Accel only works with ReWAS, so I've actually never used it. So I could just call it there with mouse acceleration. But as you may have noticed, there was a lot more stuff on that linear acceleration page. So now let me explain to you why you probably have a very good reason to hate linear mouse acceleration. Now, it's called mouse acceleration for a reason. It's simulating the real physical action of accelerating a car. It's like physics. A lot of the same principles apply here. And because we're simulating physics, that means we can measure things that are physics related, starting off with velocity. Now, I've labeled this gain because I used all of these pages to reverse engineer raw Accel's gain feature, but what I'm showing here is essentially velocity. And you can probably immediately notice something. Unlike the acceleration curve itself, the multiplier, our velocity increases dramatically until we reach our maximum sensitivity, and then it abruptly drops. Your brain can feel this. In fact, there's an even more accurate measurement to show what it is you're feeling. That's called jolt. In physics, jolt is whenever you're getting pushed back in the seat of your car as it accelerates. So in a way, jolt represents gravity. So as we're accelerating, we're experiencing a certain amount of G's until we hit our maximum speed, at which point we abruptly stop being pushed back into our seat. So by measuring these two extra details, yeah, I think this is objective proof as to why linear mouse acceleration feels terrible. Because I believe the human brain is essentially a linear relativity calculator. Like as we experience our games and stuff, your brain is constantly measuring these two things in relativity to your controller motions. And so if your camera is moving faster than your brain expects it to, your brain will experience a sudden jolt when you hit your maximum sensitivity, and that sensation feels terrible. So the question is, can we fix it? Yes, we can. And that's something that raw Accel figured out. It took me a bit to figure out what it is they were actually doing, because I'm not gonna lie, I'm not a math magician. I'm not that good at math. So it took me a little while, but I think I figured it out. Instead of using sensitivity directly, like we would here, with raw Accel's gain feature, raw Accel says, what if instead of representing our acceleration curve, what if this curve represents our velocity? So if our original curve is now velocity, we can reverse the calculations to produce this new sensitivity curve. And now we use this curve for our sensitivity, thus tricking our brain into perceiving this curve as our velocity, and in turn giving us this final jolt curve. Just like before, we're still getting pushed back into the car, and then once we reach this point, we gradually descend. And that is how gain works, at least I'm pretty sure. But as you can see here, this is not as smooth of an experience as we can possibly have. We can make things even smoother. Okay, pop quiz. If you roll an object down each of these lines, which object will reach the ground first? Have your guess locked in? Here's the answer. What I just showed here is a thing called the Brachistochrone Problem, which is also related to something called Snell's Law. It basically just shows that the fastest path to any point isn't actually a straight line. Now, I bring this up because if I flip this upside down, it kind of has a neat correlation to the next thing I'm going to show. So our solution to having a smoother acceleration experience is to use a curve. In this case, it's a cubic. But if I show the gain and jolt curves, you can see that our gain still has a pretty nasty bump in it, and our jolt is a linear straight line. So just like we did before, we're going to pretend that our sensitivity curve is the velocity, and this is our sensitivity curve now, giving us the smoothest possible jolt. And by the way, you do have to ignore this spike at the beginning here. That's just a quirk of how this stuff is calculated. So this next curve doesn't actually need to do the gain trick because a power curve basically curves into infinity. So you never actually flatten out to feel a bump. Unless of course you artificially add a flattening point, at which point you will. So this is what a power curve looks like. So ignoring the jolt spike at the beginning, you can see that a power curve is already smooth, but nonetheless we can apply the same gain settings. As you can see, the sensitivity we experience is now slightly lower than the settings we are using, being just below our target of 4, but our brain will still perceive a sensitivity of 4. The last curve that I mapped out is a sigmoid, and I did this for one specific reason, the offset setting. For every other curve type, I honestly don't recommend using an offset ever. And to show you why, let me use natural as an example. So here we're looking at the natural curve without gain, and this is what it looks like if you implement an offset. Using an offset basically guarantees that you are going to feel a massive spike once your curve actually kicks in. It's the same for linear and it's the same for power, even when you're using gain. You'll feel it on the jolt curve, although it does get smoothened out a little bit. However, because of the natural properties that a sigmoid curve has, without gain, a sigmoid retains a smooth transition. And we can apply gain to sigmoid as well, and that looks like this. And as you can see, that's pretty smooth. So now that I've explained the importance of curves and gain, I can go ahead and take a swing at explaining to you why, although Steam Input's current precision speed option feels great, it's kind of a double-edged sword. The way Valve describes precision speed tells me that they are using acceleration. So when you're below your threshold, your sensitivity is being lowered. The difference is, they are also keeping track of the distance your mouse should be traveling if you weren't using mouse acceleration. That way, when you cross the threshold, Valve instantly re-adds in the distance that your mouse would have traveled if you were using a flat sensitivity. And so conveniently, this completely negates the jolt that you would experience from that transition, tricking your brain into perceiving a flat sensitivity. And that's what makes it feel so good. But that means this is also a double-edged sword for precision, because if your window is too big, there's a chance you can completely skip over a target. So you want to use as little of this as possible. So now that you understand the importance of curves and gain and all that stuff, I can explain to you what I was trying to do here. Basically, all I'm doing here is I'm trying to replicate a natural curve by combining steadying with mouse acceleration. Visually, that would look like this, where I'm using steadying to lower the sensitivity to 0, and then I use mouse acceleration to multiply that steadying, and then combining the two, we get a final simulated sensitivity that kind of has a curve in it, although it's not perfect. And so until better acceleration options are created for gyro specifically, this is what I've been using. Not these settings here, but settings similar to this. And so that brings me to the next thing that I made. Up here in my links, I have something called Gyro Gravity. This is a custom mouse acceleration program I made specifically for gyro. Now, I made this because raw Accel only works with ReWASD, and I wanted something that works with Sim input and JoyShock Mapper.
So, I'm gonna be real with you guys. I literally don't know how to code. I am not an engineer, and I have never worked at any gaming companies, like Blizzard, for example. And And so I slapped this thing together with the help of AI, and it barely works. But it does work, on desktop at least. So if you want to try it out, just go to the release page, download the RAR, and run the exe. And this is what you should be greeted with. To begin, I've listed off the 4 curves that I think are most important. There's probably more, but these are the ones that I landed on. And the ones that I just showed. Natural, linear, power, and sigmoid. Now, natural is the default because I do agree with raw Accel in that natural has all of the traits that we want out of a good acceleration curve. And it's the most simple one to actually math out. Here in the middle, we have dots per 360. So if you're going to try this out, you can only really use this on desktop. In game, this thing stutters and disconnects a bunch. I don't know why. I don't know how to code, but it does work perfectly fine on desktop. So what I recommend is that you simulate an in-game sensitivity on your desktop and use that number here. This ensures that things are being scaled to degrees per second. Although to be honest, I'm not sure how accurate it is because, well, I'll get to that. Now, on the opposite side, I have the curves listed again, this time for the vertical sensitivity. This is something I sort of realized after the fact, because originally, I was only going to synchronize the setting. So that way, if you want, as most players do, using different gyro ratios for vertical and horizontal sensitivity, you could separate those two. But while making this, I realized you could even go an extra step and use completely different curves for both axi. Now, why you would want to do that? I have no idea, but it's a thing that you can do, so I figured I'd add it as a feature, although I can't imagine anyone actually would. So it is best just to leave the curves synchronized. And if you unsynchronize your settings, you can reduce your vertical sensitivity, and you can adjust all of this separately from your horizontal sensitivity. So just like raw Accel, I have a gain switch here. So if you want to use just a straight up basic curve, you can. If you're used to linear, the way that linear works right now, you can use it. And linear has an enable limit here, so that way your sensitivity actually caps off. That's something I was kind of experimenting with, and I'm not even sure uncapping it works properly, but theoretically, this lets you increase your sensitivity into infinity versus just keeping it hard capped. So back to natural. You pick your target gyro ratio, like you normally would in game, and underneath that, I have a setting for mirror sense. This is just what I showed earlier in the video. If you're using a sensitivity of 4:1, then the lowest sensitivity I recommend is 1:4, so 0.25. This just automatically applies that. So instead of lowering your sensitivity all the way down to 0, you lower it down to a mirror sensitivity. But the way this program works, and it is slightly different from other Accel programs,
you actually can lower it all the way down to 0 if you want. So now I've effectively combined steadying with mouse acceleration. The next setting is your target degrees per second, and below that were some recommendations that I originally had, but I realized my old recommendations were flawed because my logic was flawed. These numbers down here are based on the square of your target gyro ratio. So if you're playing at 4 squared is 16. And early on in my testing, I realized that this was a decent sort of range to stay in for whatever sensitivity you're using. But I later realized that this was just kind of a pure happy coincidence, because the problem is degrees per second is an arbitrary measurement. This could be degrees per minute, degrees per femtosecond, degrees per arc minute, or whatever. Arc minute's a distance that light travels and whatever. But you get what I'm saying. So ignore this, because instead of this, what I realized is we need something that is more direct to you personally, of what your needs are as a player. And so that's why I added this down here at the start peak record. So down here, if you hit record, my program now starts recording the average peak movement of your controller. And it basically gives you the average shakiness of your controller. And you do have to make sure your dots per 360 is properly calibrated. I can't say how accurate this is though, because it does seem to be off by about 2 degrees per second, depending on the sensitivity. So let's say you want to measure how much shakiness there is when you're spamming a single fire weapon. All you got to do is start spamming away when you hit start peak record. I feel like that's a more relevant measurement of what your target degrees per second should be. At the end of the day, I don't know what you're doing or what you want out of your gyro. That is up to you. If you're just going to use Accel to stabilize the shakiness out of your aim, something like this would be the lowest target degrees that I would recommend. And this is just going to vary from person to person. In fact, the lowest amount that I'd recommend you record here is just holding your controller. Hit start record and hold your controller still, however you play your games. So even when you think you're holding your controller perfectly still, there's movement. So the x-axis here seems more accurate, because when I've measured this, I'm usually about around 2 to 3 degrees per second of shakiness from just holding my controller still. And so I'd call that range like your ambient resting point. And the next thing you could record, if you really want to, is your actual flick speeds. Maybe you want your Accel curve to just reach your max sensitivity at your maximum flick speed. Just hit record and start flicking your controller like you would if you were actually playing a game. So my recommendation is to flick to the corners of the screen. And yeah, that seems about close. Around 200 to 300 degrees per second seems to be the usual result for me. And I'm not trying to flick as fast as possible, I'm just trying to flick the way I would if I was casually playing a game. And so something like this is what I would recommend for choosing your target degrees per second. And then the next setting for this is offset, but like I've said before, it's just something I actually don't recommend. To be honest, if I were to natively implement something like this, I would just get rid of offset entirely. It's completely unnecessary, with the exception being for Sigmoid. So linear pretty much has all the same settings, except for enable limit like I just showed earlier. And the power curve has an extra setting to adjust the exponent. Now, I'd like to take a small tangent here, because I've been pretty confident for the longest time now that Steam Input's old acceleration options are a modified version of a power curve. So here's a completely different sheet where I basically tried to manually measure what those curves are. I was told a ways back that Steam Input's curves approximately flatten out at 100 counts per second. However, that never quite felt right to me whenever I tried to use that with linear Accel. I always felt that around 40 counts felt best. So after tediously and manually trying to measure this, this is what I came up with. This is roughly what Steam Input's high setting is, its medium setting, and its low. I also tried to measure Steam Input's new options, but this might be out of date by now. In fact, I'm pretty confident that in the new UI, the current settings are just a visual bug, because the corresponding settings are the joystick options for old Steam Input. And if you actually try and use the new acceleration settings, the last time I measured it, it basically just increases your sensitivity to infinity. And now the last setting is Sigmoid, which is just as straightforward as the natural curve with all of the same settings. And you can see the difference in the jolt meter here. Unlike natural, I have the gain feature off, although that probably should be on by default now that I think about it. But because Sigmoid feels so similar to natural, it's just a matter of preference. Although when I was making this program, Sigmoid required the most math, and so I don't know if that means it'll use a lot of processing power. Like, it's working here, but in an actual game where a lot of stuff is going on, I don't know how efficient a sigmoid curve would be to use for actual gameplay. And well, there you have it. This is kind of what I think acceleration should look like. Although, I will be honest, there is one more thing I'm going to cover in my spreadsheet, and it's gyro ratios. So at the top here, I have this calculator that just lets you very quickly determine what setting you should be using in Steam Input if you're trying to simulate a specific ratio. All you have to do is type in either the ratio or the sensitivities that you plan on using. And this will tell you what vertical scale you should be using in Steam Input. For DroidShock Mapper, you can calculate an equivalent sensitivity based on your horizontal sensitivity. So based on whatever ratio it is you have on the left, this automatically gets scaled. Now on the right, I have what I call 2D correction, because if you are using Rubberband or Wiimote simulation and you're reducing the vertical scale, you'll need to recalculate your vertical scale again to make sure you're simulating the correct vertical scale. That's confusing. And this is where I gotta be honest. Like, the ratio stuff is a cool, unique thing to gyro. However, I'm not sure it's completely necessary, because you already have two sliders, one effectively for horizontal sensitivity and then another for your gyro ratio. Why not just make the second slider a vertical sensitivity slider? Like, I think that would be a much more direct and simple way of setting up sensitivity. You wouldn't need to do all these extra calculations trying to figure out exactly what the ratio is doing to your sensitivity. But again, that's just my opinion. And that's all I'm going to be covering. There are two more things in this spreadsheet that I decided to skip over because this video got way longer than I expected it to be. And those other two things are related to Steam Input's new joystick options, since they did replace the old one. So I need to actually use those options. And that's pretty much all for this video. I hope all of my rambling made sense, and I hope that some devs are watching, because I think there is still plenty of room for improvement when it comes to implementing gyro. A bad first experience can really sour people off of something, and I think gyro has a lot of room for improvement. So these were most of my ideas for gyro, but I do have other things that I want to talk about. So if you're interested, you know what to do. Until then, catch you next time.